Testing, 1, 2, 3. Testing. Testing, testing, testing. 1, 2, 3. Testing, testing, testing. Manage participants. I don't see any participants. Maybe we'll wait here. It's a little early. It's only 9:17 or 18. So we're not here yet. Mute all? Do I want to mute all? No, I don't want to mute all. Join audio, share screen. What am I supposed to push here? Dang it. Testing, 1, 2, 3. Is there anybody out there in listening land for Strength of Materials 9:30 at Thursday? We don't have any customers. Meeting topic, host. Join audio, share screen. Am I supposed to push something? Invite others? Yeah, we'll just wait, I guess. Somebody log on here. Nothing's happening. Usually Kristen's on there by now. Where's the little thing that says start meeting? Let's see if we can find that. Oh, it says start video. Maybe that's what. Now let's try that. Start video. Oh, there we go. There's the whiteboard. That needs to be adjusted. That's not right. Yeah, that's pretty good. There's the whiteboard. Is that clear? Gosh, I hope you guys can see that. Okay, well, we're just going to wait a minute till people show up. Maybe I've entered into an alternate universe. Okay. Well, I'll just relax. If nobody shows up, tough beans. I can't help it if nobody shows up. Thursday, April 16th. The topics. I know I could write down the topics for today. Let's see, what am I going to talk about? Topics for today. We could have a tiny review. I wonder what we had for homework. I forget. Oh yeah, it was at 8:10, and I graded a bunch of them. And you guys did really good. Good for you. Well, today's topic is going to be stress transformation. Today's topic. Stress transformation. Yep. Hey, we got a customer. Hey, hip hip hooray. Uh, Dalton, welcome. Welcome, Dalton. You're supposed to say hi, Mr. Griffin. He doesn't have his mic on, I guess. I haven't muted everybody, have I? Let me see here. It says mute. Am I supposed to click on that? I don't want to invite people to join the meeting. You guys are already invited. I don't know what that is. Hey, Dalton, say hi. Well, the other topic is Mohr circle. So that's today's topic. And so far, I only have one student, and it's 9:25. Maybe they're sleeping in. Oh, there they are. There's Dalton.
I had to go get some coffee.
I don't blame you a bit. That's a good idea. I wish I could drink coffee. I used to. What brand do you use? One of the fancy wancy ones, or just plain old Folgers?
We used to use Folgers, but we get oh shoot, we get it from Kroger. We have to get it from Arkansas, where my brother is, but I don't really remember what the brand name was.
You really like it?
Yeah, my parents and I are addicted to it.
Well, Folgers isn't bad.
I like Folgers.
Yeah, it's pretty darn good. I knew a guy around the corner from me where I lived that was a dealer distributor, and after a certain date, uh, they can't sell them anymore. And he had a pile of them in his garage, and he gave me a armful of free out of date Folgers. And hey, the out of date stuff tastes just as good
This
as.
is good.
Yeah.
I bet.
Well, you might be my only student today, Dalton, the way things are going, but we'll see.
I get extra credit, right?
You should. You deserve it. But at least this thing is working.
Yeah.
Well, let's see. I'm gonna pin me, I think, as they put there's three little dots there. What do I do with those three little dots? Maybe click on them?
Yeah, I think you click it and then it should say pin video.
Yeah, there it goes. It says pin video.
Yep.
By Jove, there it is. Hey, Cameron, we got another customer. Cameron just showed up. Good. Hello. Hola.
How are you?
Uh, I think I'm okay. So. I'm not too bad. Always, I'm kind of nervous. Not about teaching you guys this stuff, because I love this stuff and understand it, but I'm nervous I'll push the wrong button on this computer. You probably can't relate to that.
Well, it's understandable.
Hey, there's Allison. We've got another excellent student that just showed up. Allison is here. She's got her mute thing on, though. Well, we got 3 minutes before it officially starts. The topics for today are stress transformation. I'll try to make sense out of it for you here in a minute. We're going to have a little teeny tiny review here though first to make sure you guys can do some of the stuff we've studied. We're going to start off with a little tiny review here. So this is just old stuff that you all know and love. Let's say you had a 2x4, 2 inches by 4 inches. However, we'll make it out of A36 steel, not wood. Well, that's a cross section. Hope I can do a better job of drawing that. There we go. And let's suppose you had a bending moment. Now, I like to draw my bending moments with double arrows. And say the bending moment was 10 kip feet. And also, let's say we had some shear acting on it. Suppose there was a shear force, and I'll make up something maybe, I don't know, how about 40 kips? Now it's a beam. You understand now, this thing's going back in space here, and you're looking at the cross section of a 2x4 inch beam, only it's steel. Now, we're having a little review here while people log on. Oh, I got some more customers. Look, Caitlin, Daniel, Gavin, Eric, welcome. Bienvenido. You're welcome. Bienvenido. Okay. Now, what I want you to do here for a review here is to find the, we're going to find the bending stress and the shear stress, but the question is where. See, you gotta tell us where, because look, remember at the top and at the bottom there is no shear stress. The maximum shear stress on a beam that's bending is in the middle. The maximum shear stress is in the middle. It's maximum shear stress. Remember that, I don't know if I took you on that little field trip to the atrium there around the corner from our classroom. There's a beam that's split in the middle because of the shear stress. I don't remember whether I did that with you or not. And now the normal stress, it's just the opposite. It's maximum at the top and bottom, and it's 0 in the middle. Here, I'll write that for you visually oriented people. It's 0 in the middle. We probably should say, what's the word instead of middle? Centroid. Yeah, because not everything's a rectangle. It's 0 at the centroid. And it's maximum at the top and the bottom. Well, it'll be maximum at the maximum distance from the centroid. Top and bottom are the same distance from the centroid. Now the shear stress is 0 at the top and bottom. Hopefully I'm boring you and you know all this. It's 0 at the top and the bottom. But see, it's maximum at the centroid. See, the normal stress is maximum at the top and the bottom. I just spelled bottom. It's not BOO. That's not right. There you go. And the shear stress is maximum at the centroid. They're just kind of opposite. And y'all, little Southern talk, y'all understand that. I'm just repeating stuff that you already knew. Can you read my writing there? It's awful small. Well, I hope you can read it. If not, speak up. Let's see, we got Eric, Daniel, Dalton, Caitlin, Cameron, Allison, and Kristen's back with us. Hey, Kristen, have you had your coffee this morning?
I'm working on it, sir.
Okay, now you have to decide where you want to talk about. Well, I'm going to pick us a spot and we're going to do it. We're doing a little review here for a minute. And then we'll get into our main topic, which is stress transformation. But let's pick this spot right here. Now, if this is 4 inches, that distance from there to there is 1 inch. You're 1 inch from the centroid, and you're also, can you see that you're 1 inch from the top? And we want to find the normal stress at that location. We could give it a name. I don't know. How about calling it point P? There you go. We're going to find the normal stress at point P. Okay. Well, you know the equations. Here, let me write the equations. You know this one here, it goes minus my over I. And this one goes VQ over IT. Now these equations have names, and you know these equations by heart. You know that this one here is called the starts with F.
Flexure formula.
Yay, it's the flexure formula. And this one here is called the shear formula. All right. Well, notice I is in both of them, so we're going to have to get I. Well, that's not a problem. That's just 1/12 2 inches, 4 inches cubed. Man, that's it. Okay, I could almost do that in my head, but no, that's too hard. I can't do that in my head. Okay, I got an answer. I'm getting 10 point, a bunch of sixes, inches to the fourth. Hey, looky here. We just figured that out. And the bending moment is given. Look here. We gave you the 10 kip feet. And Y, now what's Y? Well, that'd be 1 inch. See, if you want to talk about point P there, then that Y is 1 inch. Okay, well here, let's put in the numbers and get it. Now the minus sign, what that's going to do is tell us it's compression. I've told you guys that before. When you have a beam that's sagging and you got a load on it, it's got compression on the top, tension on the bottom. See, if that Y had been minus, then you would have had a negative, and that would be minus, that would give you positive. And when the Y is minus, you'll be down here, you'll have tension on the bottom of the beam. And you understand that, don't you? All right, well, let's get the answers. Let's see. Hey, why should I do all the work? I'm going to shut up and I'm going to let you do this. I'm going to give you a minute and a half or something. I'm just going to relax. I don't drink coffee anymore, but I can have a virtual pretend cup. I'll have my virtual pretend cup of coffee while you get this answer for me. On your mark, get set, go. Hopefully you're doing that. Let me write out the numbers for you. Something's not right. I'm not doing something. Oh, here's my problem. I forgot the feet. See, that's 10 kip feet. There we go. Now here's what you got to do to make this work. If you just do that, you're not going to get the answer. You got to multiply by 12 inches over a foot, or else you've just lost some points on your final exam if you have a problem like this. We don't want that to happen. All right, now I'm going to get the answer now. I gave you a little time. Did you get 11.25 KSI? And I'm waiting for an
That's what I got.
Yay! Hey, we got Ross and Mohammed now. Pretty good group there. I need another
Yep.
Yeah, I heard a yep. That'll do it. Okay, now we're going to do this one. Now we know V. This is V right here. See, V is 40 kips. Q. Oh, here's that Q thing gives students trouble. It's called the first moment of area. I we've got. V we've got. V is 40 kips. I is sitting right here. Now T is 2 inches. So I know that. Oh, it's that stinking Q that could give you problems. Again, I think I'll shut up for a minute and a half. And I want to see if you can do that. We're trying to find the shear stress at this location P. I called it P. It's right here. It's kind of 1 inch from here. That's where it's at. We want to find the shear stress. See if you can do it. On your mark, get set, go. Well, here, I'll write it out for you guys. We got 40 kips times Q, 10.66 inches to the fourth. The thickness is 2 inches. Man, if we only had that Q thing, we could do this. Do you remember how I told you to find that cue, that first moment of area? My daughter got me a couple of colored pencils. What you do is, to find this cue, you draw a line through the, well, that's not very dark, is it? I don't know if you guys can see that. It's too faint. Let me try this blue one. I can see it, but I don't know if you guys can see it. Let's see. I'm going to try it. There you go. Now, the way I tried to tell you to find this cue thing is you draw a line through the place where you want to find the shear stress, and then you color everything above the line. There. I colored everything above the line. And for rectangles like this, Q is just going to be Y bar A. It's just going to be the distance to the centroid of your colored area, which in this case is 1.5 inches. And the area is a 2 inches by 1 inch area. And I'm getting 3 inches cubed for my value of Q. Now we know what Q is. It's 3 inches cubed, and you can solve it. And I'm going to do that now. And I'm going to get the shear stress at that location. Well, I got an answer, and what I got was 5.63 KSI. And I'm going to wait till I hear some uh-huhs.
Uh-huh.
There's one.
Yes, Professor.
There's 2 of them. I need one more. Hey, what about my friend Kristen? Kristen, did you get your coffee, and can you give me an uh-huh?
Yes, sir. On both.
Yay, great. Okay. Well, that was kind of a fun little review thing there. What I'm going to draw now is called a stress element. I've told you about these before, but we're going to draw one. I need a little room here someplace. We'll say goodbye to all this stuff. That was fun, wasn't it? I need a little room right in here. There's a little bit of room. Now what we're going to do is we're going to draw a little stress element right in here. It kind of looks like a little sugar cube. Okay, here I'll draw I'll zoom in on it. See, this is just an enlargement of this little, what they call a stress element. You'll see them all over your book. I know you guys have been reading your book. It's called, that's not how you spell stress. It's called a stress element. And I tell you what we've discovered. We've discovered there's a normal stress. It's a tensile normal stress, because this thing is on the upper half of your beam, Remember at the top, no. I'm wrong. It's compressive normal stress. And this answer here should be negative. Do you remember the equation had I erased it, doggone it. But the equation had a minus my over I, didn't it? And see, when y is positive, the answer comes out negative. And so you have a compressive stress on that stress element. Now the shear stress, and I tell you how big it is. It's 11.25 KSI. Now you also have a shear stress, and it's going down like this. That's the shear stress. And how big is it? Well, it's 5.63 KSI. That's a stress element kind of enlarged at this point P in your beam, and it's got both. It's got normal stress, which happens to be compressive, and shear stress. Okay, great. And let me make a little room here. I want to draw this stress element. I want to just draw it like this. You see this normal stress? It's going like that. What I'm doing is I'm kind of turning this around, and the shear stress, that's the normal stress, and the shear stress is going, I'm kind of looking at it from over here. It's kind of hard to explain, but an observer over here looking at this thing will see the shear stress going down on that side and the normal stress. Hey, look, the sum of the forces on any body in this class has got to be 0. And so there has to be a compressive normal stress acting on this back side. It's kind of hard to draw back there, but it would be going that way. Now on this shear stress, it's going down. See, force is equal to stress times area. Or if you're doing a shear force, it's shear stress times area. And guys, you can't just have one force on this thing. If you got a force going down, you got to have a force going up. So there'll be a shear stress acting on this backside. Kind of hard for me to draw. I don't know, we can do it in dashed lines, maybe going up on that backside. But now we got a problem. Do you see how this thing would start to spin? Nothing spins in this class. So you have to have a shear stress going that way. Well, now you got another problem. You'll have a force going that way if the shear stress is going that way. So you got to have, there you go. There's your stress element. You got two compressive stresses here. Nothing's going on this way. You don't have any, I don't see any stress pulling or pushing that way, do you? But you do have shear stresses, 4 of them. You have to have 4 of them for equilibrium. So we've talked about reviewing, what is it, the flexure and the shear formulas. We've talked about shear elements. Now I want to do another review thing. I want to go back to something we studied a while back, unless there's a comment or question. If you have a question or comment, I'm listening. Is my microphone working okay?
Yeah, it's working fine.
Wonderful. Well, okay. I don't hear any questions or comments. You seem to understand that. I'm going to erase all this and do another minute of review, and then we'll launch into some new stuff here in a little bit. We're still doing a little tiny bit of review here. I put another homework assignment on Blackboard. I've been grading your homework assignments. You should be be aware of whatever grade you got on your homework that you submitted to Blackboard. Hey man, it's great. I got all my strength and materials homework from students in one big glob, and I can just go through it in a hurry. And it's not driving me crazy like it was when everything was on the email. Okay, well, now next topic, this is a review thing. And it's something we studied way back. January, February, I don't know. Yeah, here we go. If you had a rod, now it could be circular, it could be a square, it could be all kinds of shapes. And let's say it's under tension. Okay, so you'll put a force there. I like the symbol P for that force, but I think the book uses an N, maybe for a normal force. Maybe we should do what the book does. Suppose it was a square, then it would have an area. There you go. Trying to draw that force there, it'd be acting in the middle. There you go. Kind of messy there. All right, and then this would be, oh gee, you get the picture. It's a, oh, we tried, it's a little wavy there. It's a square rod under tension. And we're going to call this area here A0. So if you sectioned it perpendicularly in here like this, and you looked at a perpendicular cross section, and you took a section there, you would have that same tension throughout the piece, and your normal stress at any location in here, if you cut it perpendicularly, is just your force divided by your area. And that's pretty boring, we know that. But back in February or whenever it was long ago, we talked about what happens if you cut it at an angle. See, like if you cut this at a 60-degree angle, which would be about kind of like that. It's kind of hard for me to draw that, but I'll try. See that if you sliced it like that, you're going to discover that you're going to have a normal stress going this way, but you're also going to have a shear stress going that way. And I didn't draw that very good. If that's 60 degrees, let me try drawing it again. You see, there's some hidden lines in here. We're gonna put these hidden lines in here. There we go. There's the hidden lines. Yeah. And so if you cut that at 60 degrees, oh, gee. Trying to cut it at 60 degrees. It'd be like that. All right. Oh, I'm not that swift with the artwork. That's not too bad. I think you can almost see that. If you cut that at 60 degrees, it's got a bigger area. And so you can't divide by this area here. I think we derived this. I'm not going to go back and derive it again, but we came up with these lovely equations. This one goes like this. Hopefully you have this in your notes from long ago, where this is the angle theta here. And the shear stress is equal to this here. We derived those equations long ago. The moral of the story is you have normal stress and shear stress at different orientations inside your piece. Let's put some numbers on it. Suppose this is 1 inch by 1 inch square steel rod, and this normal force is we'll make up something. We'll say it's 20 kips. Well, the stress right here, if you're interested in the stress right here, that would be 20 kips divided by 1 inch times 1 inch. I get 20 psi. I hear a sound. It's sort of like somebody slurping up some vanilla pudding, but maybe that's not what it is. Okay, now what if you slice this at an angle here? Well, let's do that. Oh no, wait a minute. You're supposed to use N for the normal force, like the book does. Okay, well then this would be somebody's still slurping something. Divided by, well, that's just 1 square inch. Ah, but you have to go cosine squared of 60, don't you? What is the cosine of 60? Is it a half?
0.5.
I think it is. And when you square it, a half squared is a fourth, isn't it? You know what I'm getting? I'm getting 5 KSI. You guys can plug that in your calculators if you want to. We do have a normal force at that orientation, at that, if you slice it there at 6, I slice it at 60 degrees. And you do have a normal force. It would be going perpendicular to your area, kind of like that. Yeah. That's what normal means. It means perpendicular. But now you also have a shear force. Let's see what that is. That's going to be 20 kips divided by 1 square inch, sine of 60, sine of 60. I don't know what that is. But
Is it? I thought it was sine cosine, not sine sine.
You're absolutely right, but I wrote it right. I said the wrong thing with my voice, didn't I?
No, later on in that.
You wrote it wrong as well on the
I
left there. It
wrote
says sine
wrote it
sine.
wrong. I did not write it wrong. It's you
Move
know
your
what?
hand to the right. Keep going where you wrote it out there. Does that not say
Oh,
sine sine?
honk and thank you point goes right there. I am wrong, and I'm so proud of you. I did write it wrong, but I got you. You're my backup. Okay, now we're going to calculate this shear stress in there. Here goes. 20 times the sine of 60 times the cosine of 60. Boy, Jove, I'm getting an answer. There is some shear stress in there, and it's 8.66 KSI. You double check me on that. Make sure you got that. Ooh,
Yes, sir.
you got some shear stress in there. Now, I'll show you an interesting thing. In your book, I probably showed you this long ago. This is all leading up to today's topic, by the way. On page 89, on page 89 in your book, something we studied long ago, back when we were all younger and better looking. Page 89. Yeah, there it is. There's a picture of a steel rod that they have put under tension, and they have stretched it until fracture. And there's a little room over here on page 89. On page 89, you'll see this. You'll see this steel. It broke in two. And there's a 45-degree angle here. It kind of goes down there, sort of a pit there. Can you sort of see that? Kind of hard for me to draw, but the picture is pretty good. There's a 45-degree angle.
My baby.
It turns out the shear stress is maximum when these angles are 45 degrees. Any other angle, you'll get smaller shear stress. So naturally, it's going to break. If it's weak in shear stress, it's going to break with a 45-degree angle. And steel and other ductile materials, steel is ductile. It's not brittle, it's ductile. And ductile materials are weak in shear stress. And if you put them under tension, what will break them is the shear stress. Isn't that interesting? Yeah, fascinating stuff. Now, we could spend a lot of time finding the maximum of this equation at different angles. That's something you could do. Take the derivative of this with respect to theta, set it to 0, maximize it, and you'll find that shear stress is maximum when theta is 45, and ductile materials like steel they'll break at the 45-degree angle. Okay, I think it's pretty much time to get into the stress transformation equation, but I hope we've learned that inside a piece, you've got somebody's still slurping that vanilla pudding. I can hear them slurp. I wonder what that noise is. Now they're gargling.
Brandon.
Okay, inside a piece, you have normal and shear stresses going on inside the piece. See, we could have picked a different angle. We could have picked 10 degrees, 20 degrees, 30 degrees, and there's normal and shear stresses at all those angles inside your piece. Yes. Somebody was trying to say something, but nothing came through to me. All right, well, we're gonna tackle stress transformation now. We did a little review of ancient history here. Unless you have a comment or question. All right, well, here goes. Let's get rid of that. We had a little review there. It was fun. We have a thank you point, and we appreciate the help. Now, this stuff here is called stress transformation. It's on page 450 in your book, page 450, 451. And what they've got there is they've got a view of a stress element. There it is. We've just talked about stress elements. And they've given these symbols. They call this the normal stress in the X direction. Of course, you'd have to have an equal and opposite in this direction. It's possible you could have a normal stress in the Y direction, and you could have a normal stress. You'd have to have one down here, equal and opposite, for equilibrium. And then they put some shear stress acting on your stress element. We'll call that tau xy. It's in the xy plane. And here you would have tau xy. You have shear stress. Now, what they're talking about now is, what if you looked at a different orientation? What if you rotated this thing? I'll try to rotate it some angle here. You see what I did was I rotated it some angle theta. See? And what I'm looking at now is, what would a stress element look like that had been rotated through some angle theta there? Well, you're going to have normal stress, only they gave it a different name. They call it sigma x prime. In your book, those of you that have books, do you see a sigma x prime anyplace? I do. Yeah, there's a sigma x prime. And then, of course, there would be one going this way too. And then you have a tau x prime y prime. Of course, there'd be some down here too. It's getting kind of messy. Do you see a tau x prime y prime? I see one on page 451. On page 451, I see a tau x prime y prime. I'll give you time to look. Now they've come up with these stress transformation equations, because what we're going to find is, we're going to find the normal stress and the shear stress at a different angle. Different angle. I would love to go through the derivation, but you could. It's right there on page 450. Well, 451 really. Let me tell you what they did. They took a slice here. They took a slice. There we go. And they looked at just that slice here. Here, let me color it. I'm coloring this blue. My daughter gave me a blue pencil. And what they did was just forget everything else. And they did the sum of the forces is 0 on that blue slice. The sum of the forces in the X and Y, but more importantly, the sum of the forces in the X prime and Y prime. See, Y prime would be going like this. See, X is going this way, but X prime is going that way. Y is going straight up, but Y prime is going that way. See, they got those. And here's what they got. I'm going to spare you the agony of the derivation. It's right there, though, 451. It's clever. See, what they did for these forces is they said you take the normal force times the area, that gives you a force. This shear force times the area, that gives you a force. And they got the sum of all the forces acting on that blue kind of a wedge. And here's the stress. I'm going to erase this because I need the room. But you can read about it. And here's our equations. A little bit ugly, but not that bad. It doesn't scare us too bad. This is going to give us the normal stress in an X prime direction for any angle. That's enough. There's also one for the shear stress, but I'm going to spare us right now. We'll come back to there's another one that has the shear stress in the X prime, Y prime plane, but we're just going to look at this and we're going to do an example here. And I'm going to do something I've never done before with you guys, and I'm a little bit scared here, but my daughter told me how to do this. She's at work, but she wrote it out for me. She says, go to the bottom of the screen and push share screen. Okay, I'm going to do what she said. I'm going to push share screen. There, I did that. And then go to the file. Oh, gee. Go to the file. What do you mean, go to the file? Oh, man, I'm supposed to go to a file. Maybe it's this. I bet it's in this documents. Yeah. Hey, that's it. Double click, maybe? By Jove, there it is. There's the file. Now, what I want is Google Drive. What do you mean, Google Drive? I don't see anything that says Google Drive. That's what she said. I'm just reading her instructions. She said, I think I did what she said. Now we're going to find the file that I want to share. Now, the file I want to share is the one that says Moore's Circle, I think. Let's see. I got to find it here. Just a minute. I'm looking at all these files. Bear with me, people. Bless you for bearing with me. Oh, there it is. Probably double click. Well, I clicked on it. Yeah, there you go. There's that little circle thing. By Jove. A pop-up will come up at the bottom. A pop-up will come up at the bottom, and you need to select Share to Everyone tab. Okay, I'm kind of scared here, guys. Share. What do you mean Share to Everyone tab? Where does it say Share to Everyone tab? Oh no, I don't see it. Gabriel, do you know where this Share to Everyone tab is?
You might need to double click on the more circle again.
Okay.
I don't think it loaded
Oh,
from what I can tell.
well,
It might have loaded. It might have just opened somewhere else, and you're only
Okay.
sharing your documents folder with us.
if we have to, I'll do it by hand on the whiteboard. I wanted you guys to see that I put this thing on your content, and you guys can pull this up. But I'm trying to show it to. Oh, wait a minute. No, where the heck? Okay, there you go.
Professor Griffin, can you see
Yeah.
the document on your screen?
Yes, I can see the document on my screen.
So at the bottom, hit stop sharing, and then hit start sharing again, and click on the document and see if that works.
Well, now at the top it says stop sharing. I don't want to stop.
Okay, do that then.
Oh no, I've clicked on stop sharing. Now I'm back to this. I want.
Okay, so hit start sharing again, or share screen again,
Okay, I'm going to push share screen,
and then click on the more circle document if it pops up.
okay, and there it is. Double click or single click? Don't know. Double click. There it goes. And when I do that, it pops up, and there it is. But my daughter said, it says click on Share to Everyone tab. A pop-up will come up at the bottom. I don't see any stinking pop-up coming up at the bottom. Oh, I'll have to talk to her about it. Okay, well, guys, here I'm just going to have to. You will have this. Maybe that's it. Okay, you will have this. Okay, well, all right. I'm sorry. I failed. What I need is something that says Share to Everyone tab, and I never saw it. There is some stuff down here. There's a thing on files. And I don't know what the rest of this stuff does. Okay, well, let me bail out of this, and we'll do it the old-fashioned way. And now you're back with me, right? And you can see me and hear me, can't you?
Yeah.
Yes, Professor.
Good, excellent. Well, I've got this thing that I tried to show you. And what I've got here is a stress element. And you do have these on Blackboard, on content. I sent these to you, and I hope that you got them because it's your homework. I gave you a homework assignment. And I've got 6 of these, and this is the first one. And see, we can do this together. Okay, we got our stress element, and we have our shear stress. This is number one. This is number one. There's 6 of them. And it's going to be your homework. And I'm trying to explain what I want you to do with it. But see, in this case here, this is 11. And this is 3. 11 and 3 make 14. So that's really a 7. Here, let me write this out for you. Your stress at some other angle is going to equal 7 plus, this is 11 minus 3. No. Yeah, it's 11 minus 3, which is 8. Divided by 2 is 4. And this is 3. Well, there's your normal stress at any angle you want. Now really what we're interested in this class is we're interested in the maximum stress, because that's where it's going to give you a problem. The maximum stress is where the piece is going to fail. So we're interested in the maximum stress. So what angle would that be? Well, I don't know. That's what Moore's circle will tell us. Now we could make a table of values. Why don't we do that? That'd be fun. We'll make a table of theta versus your normal stress at a different angle. And we'll do this together. Let's go 10, 20 degrees, 30 degrees, 40 degrees, 50 degrees. Now you could go 0 degrees. Here, first of all, let's do 0 degrees. 0 degrees. We're going to plot up theta versus the stress at a different angle. Okay, well, when you plug in 0, what's the sign of 2 times 0? Anybody know? That'd be 0, wouldn't it? And this would be, well, what's the cosine of 0? Well, it's just 1.
That's 1.
Yeah. So what you got here is 7 plus 4. Well, that makes 11. Well, you see, that's what you get. Because when your theta is 0, we're talking about that. Now, 10 degrees is when you tilt this just a little, just a teeny tiny bit. We're going to tilt it 10 degrees. It's kind of hard for me to draw 10 degrees, but you got the message. Now we're going to plug in 10 degrees. I want you to plug in 10 degrees, and I'm going to plug in 10 degrees, and here we go. I'm doing it now. Did you get 11.78? These are KSI. Ooh, isn't that interesting? It's bigger. If you're looking at another orientation there of 10 degrees, it's bigger, isn't it? The stress is bigger. The normal stress is bigger. How interesting. Okay, let's go with 20 degrees. Plug in 20 degrees in this equation. Here we go. I'm doing it now. Well, I got an answer of 11.99 KSI, but I want to wait till I hear a couple of uh-huhs.
That's what I got.
Yes, sir.
Yeah, well, go ahead and finish this. I'll have a sip of water while you guys finish this. Go ahead, on your mark, get set, go. Uh-oh, it's starting to go back down. It's kind of like the stock market. Kind of went back down a little bit. Gee, it went down some more. I hope you're doing this because I want you to understand. Yeah, it's just going down. Are we okay on that? Let me pick on somebody. How about my friend Gavin Jackson? Gavin Jackson, did you do any of those?
Yes, I did.
Hey, Gavin, did you notice it kind of got bigger for a while and then it got smaller? Now,
Yes.
what we're really interested in is the precise biggest value, and we can get that with something called the Moore's circle. I need to show you that, but I need to erase something to make some room here. That was a lot of fun, wasn't it? Okay, well, I'm going to do the Moore's circle now. I'd love to show you how the heck they came up with this Moore's circle. By the way, they show you how to do a Moore's circle. Let me show you the page it's on. It's on page 471. On page 471, they give you a step-by-step, foolproof plan to draw the Moore's circle to find out where the maximum stresses are in a piece. And that's what we want to know. We want to know where the maximum stresses are. Can't find my eraser. Yeah, here it is. Okay, well, let me put that information over here in the corner. Well, no, I've got it, and hopefully you're taking notes. I need some room to do the Moore's circle. Here goes. Say all that goodbye. Okay, now here's what you do. You make a normal force axis. This is going to be a normal force axis. And this is going to be a shear force axis. No, I don't mean force. Normal stress axis and shear stress axis. What's weird is the shear goes this way and the normal stress goes that way. And on page 471, it says, oh gee, I erased my picture there. I've got to have this or I can't do it. This was 11. This was 3. And this was 3. Yeah. See, this is sigma y. This is tall xy. Okay, so what you do with your ruler is you come over here 11. This is your first thing you do, and you make a mark. There it is right there. I'm using centimeters. You can use anything you want. It's just make sure it's always the same. And I made a mark at 11. Now this is 3. So I got to make a mark at 3. Okay, hang on a minute. 1, 2, 3. It's right there. That's at 3. Now the distance between these is 8. Between the 3 and 11 is 8. So you put a dot right there. That would be at 7, wouldn't it? Right smack dab in the middle. That's going to be the, I think it's going to be the center. It's going to be the center of your Mohr circle. But now, going back to this 11, I skipped a step. You go over 11. That's your first step, and I did that. And then you see how this goes up 3? When they derived this, when Mohr came up with the circle, he goes down 3. If that goes up 3, you go down 3. So come on down 3, put a dot right there. This is your, what I call the anchor point. I'll call it point P. I call it your anchor point. How do you spell anchor? A-N-C-H-O-R? Is that how you spell anchor, do you think? It looks good. That's your anchor point. Now where this 3 is, whatever you did here, if you go down 3, don't get mixed up now. This is at 11, but we went down 3. Now if you go down 3 here, you got to go up 3 here. So let me put 3 right here. That puts you right there. Now we're going to draw our diameter of our Mohr circle. Here it is. That is your diameter of your Mohr circle. That's the center. If you can remember this much, you go over 11 and down 3. That'll get you started. Now we're going to draw the Mohr circle. Here goes. Well, this is 4 right here, and that's 4. That makes this 5. You know what? It's a 3, 4, 5. So I'm just going to put a bunch of 5s in here so I can make a nice circle. Well, there's 5 right there. And there's 5 right there. From the center, the radius is 5. Puts you right about there. Radius is 5. That's pretty good. Okay, now I'm going to draw my circle. Here goes. We are drawing the Mohr's circle. Ta-da. Hey, there it is. Pretty good. That's your Moore's circle for this stress element. Now, I didn't put the other values in here, but you know how they go. Now, from this, we can tell the maximum stress. This is your stress axis. The very biggest stress that you got on here occurs right there. That's your maximum stress. And if this is 7 and this radius is 5, that means your maximum stress is 12 KSI. Not only that, but it gives you the angle that that stress is at. Now remember, these are double angles. The angle that stress, all angles are measured from the anchor point, and angles are measured counterclockwise as positive. And if you have a 3, 4, 5, you guys have all memorized that angle. That angle right there, it's a double angle. All angles in this. I'd like to derive it so you could see why they're double angles. But that double angle is equal to 3687. You've memorized that, haven't you? I told you to. So the angle is half of that. What's half of 3687? Hang on just a minute. 3687 divided by 18.435. If you'll rotate this thing 18, which puts you probably about like that, artist's rendition of a rotation of 18 degrees, you're going to get the maximum normal stress. Now let's plug it in and see what it is. Remember, this was 7 plus 4 cosine of 2 times 18.435. Well, 2 times that is 3687 plus 3 times the sine. Hope you can read my writing here. Sine of 3687. Okay, now I want you to plug all that in. That's going to give you, in this case, it's going to give you the maximum normal stress, and we're interested in that. All right. Plug that in. Tell me what you get. I'm going to do it. Boy, Jove, I get precisely 12 KSI. Now, remember, those of you that took notes, which is everybody, because I know you all write down everything I say. Do you remember we got pretty dang close to 12 KSI on one of those? But what was the angle it was at?
20.
Was it 20?
Yes, sir.
It was
Yep.
20. Well, the actual angle that you need, if you want the maximum normal stress, is 18.435. 20 is close, but it's not. It won't give you the 12 KSI. Now let's go ahead and show you the maximum shear stress. There's another lovely equation for shear stress. Let me write it down. Gee, no, we're running out of time. Have you ever noticed the time just zips by in this class because it's so interesting? Okay, now here we go. We're going to write the equation for shear stress. See, you can get it from your Moore's circle. I can tell you right now what the maximum shear stress is, but here's the stress transformation equation. This happens to be on page Lost my page. Here it is. It's minus sigma x minus sigma y over 2. It's not squared. That 2 goes up there with something else. Times the sine of 2 theta. I'm running out of space here. Let me scoot that down a little bit. See, that's your maximum. Plus tau xy cosine of 2 theta. All right, now that is the equation that you can derive from that blue-shaped wedge. Some of the forces are equal to 0. And in this case here, let me write the numbers for you. This is 11 minus 3. That's 8. Divided by 2, it's 4. So what we have here is the shear stress is minus 4 sine of 2 theta plus, oh gee, I'm running into some, I might have to sacrifice a little room here, but not much. Not much. 3 cosine of 2 theta. There you go. Okay, now let me show you where the maximum shear stress is, and then we'll see if it fits this equation. It's going to be right here. See, this is your shear stress axis going this way. It's right there, and I'll tell you what it is. That's your maximum shear stress. Hey, we're interested in that. Remember that I told you about that steel rod that broke, that fractured because of shear stress? It broke at 45 degrees. But this isn't going to be at 45 degrees because that rod, all it had was tension. It didn't have any tension in any other direction. It didn't have any shear stress in any other direction. It's a little more complicated. But I can tell you what it is. It's just the radius of this circle. It's equal to 5 KSI. The maximum shear stress is 5 KSI. Now let's plug it in and see if it's true. But we need the angle. Remember, all angles are measured from the anchor point. Now here's your anchor point, P. Now in this angle, we got to go like that. And that angle is, well, it's a double angle. It's negative 5313. See, this is 3687, but going this way, it's negative 5313. So what we're going to do is we're going to plug that in. We're going to go minus 4 times the sine of 5313 negative plus 3 times the cosine of negative 5313. And let's see what we get. Plug that in. Get your calculators, plug it in. There it goes. Okay, let's see. Minus 4 times 5313. What do you do? Oh, it's a minus sign, okay. Plus 3 times cosine 5313, negative cosine. Boy, Jove, I plugged that in, and guess what I got? I got 5 KSI. Now, what angle is that at? Well, the 2 theta is negative 5313. So the theta would be half of that. What's half of 5313? Let's see.
26.565.
Good going. Negative 26.565. Very good. And so what we're talking about is if you turn this thing this way, kind of hard for me to do, but I'll try. Maybe not that much. Maybe I did too much. We're orienting it. We turned it that way 26.565 degrees, and the shear stress is maximum on that orientation, and it's 5 KSI. Let's do another one, and then we're going to have to quit. It's fun though. But before I do another one, is there a comment or question?
So on the homework, do we have to do number 1 anymore?
Why don't you do it so that you'll feel confident? But I won't grade you on number 1 because we already did it. Let's do number 2 together, and that way you'll just have 4 to do. Sound good? Here, let me make some room now. And we're going to do number 2 together, if you're happy. Is there anybody else want to say anything? And you could read your book. That's another thought. You could read the book. Wouldn't hurt you any. But try to remember the main idea here is stress breaks things. And we're interested in the maximum stress. That makes sense. Yeah, that makes sense. If stress breaks things, wouldn't you like to know what the maximum stress is? Okay, now number 2. Let me draw number 2, and then we'll do the Mohr circle, and we can find the maximum stresses with Mohr circle. Now you need to know that this was done way before the age of computers. And now with computers, it's kind of made Mohr circle obsolete in that all you got to do is click in the numbers and it'll draw the Mohr circle for you. You don't have to draw it. They'll draw it for you, and they'll give you all the maximum stresses for you. But here's the thing. If you never understood this, you never studied this, you'll wonder, well, that's black magic. Where the heck did all that come from? Well, I'm trying to teach you where it came from. That's the idea. Okay, now this one here is sigma x is 60. These are in kilopascal. And this one is, we've got compressive. We've got compressive stress of 12. This is number 2. I was going to say that's number 1 there, but that's a thank you point there. That's what that is. This is 12 kilopascal. And this is a whopping 48 kilopascal. So there's our stress element. Now remember where you got that stress element from. You got it by, well, it's directly from the shear and flexure formulas, or, well, they could be other formulas. We've studied what, about 6 or 7 different formulas that give you stress. And you know that you can have combined loading. And that's what we've been studying all semester, how to figure the stress. Well, let's say your stress element has those values. Now we're going to do the Mohr circle. So here we go, the first step. There's a step-by-step plan there. I forgot which page it is, but I told you. You make a normal stress axis. This is going to be normal stress. And here's your shear stress axis. Oops. Didn't work. I don't know, something bad happened there. Okay, now if you read that step-by-step foolproof plan that I told you about on page, I lost it, but you can go back and find it. Now the first thing you do is you put a 60 on here. 60. Well, I can't put 6. How about, well, 6 is too little. I guess I could go 6 inches. That might work. Well, wait a minute. We got to go 48 there. Yeah, 6 will be okay. We're gonna come over here. We're gonna come over here 6. Right there. And then see how this is going up 48? Well, we got to go down 48. Holy cow. No, not 48. 4.8. There you go. I'm using a scale. We're going to go down 4.8. That puts you right there. But what I did was I went over 60 and I went down 48. I really went over 6 centimeters and down 4.8 centimeters. And now look at here. This is 12, but you don't go over here to the right. See, going over here to the right, that's tension. That there is compression. So that's over here. This is negative. That's compression. So we're going to go 12. All right. Well, now wait a minute. That's just 1.2, isn't it? Yeah. That's just 1.2. That puts you right here. Sorry, this is so small, but I can't help it. We went over here. Actually, we went negative 12. Negative 1.2 centimeters plus 6 centimeters. Oh, and now wait a minute. If that goes down 48, this has got to go up 48. But I'm going to go 4.8 up. That puts you right there. By Jove. And now we are going to draw our diameter of our Mohr circle. Here goes. Diameter of Mohr circle coming up. Here it is. Okay, there it is. Now we need to find this center. Now let me think about this. From 60 to minus 12, that's 72. Half of 72 is 36, right? Oh, right, Mr. Griffin. So that means that this here is 36. And from there to there is 36. And this is 48. I need to know this radius of the Mohr circle. Let me do that. If you go 36 squared plus 48 squared, square root, help me do that. Let's see what that is. We're going to get the radius of our Mohr circle.
It's 60. It's a 345.
Boy, Jove. It's 60. Good going. it comes out to be 60. Okay, now we're going to draw our Mohr circle. Here goes. Well, again, I think what I'm going to do, if this here is 60, that's 6 centimeters. I think I'm going to make some marks at 6 centimeters. So there would be one there. And 6 centimeters puts you right there. And 6 centimeters puts you over here. A little bit messy, but that's okay. And here's 6 centimeters kind of down here. I already got a point there. Okay, I think I'm ready to draw my circle. Here goes. We are drawing Mohr's circle now.
Professor,
Yes.
where did you get the 36 and the 48?
Oh, thank you for asking. Do you remember we had 60 from here? Look, from here to here is 6 centimeters, and that's 60. And see that 12? It's a minus 12 because it's compression. From here to here, it's minus 12. Here, let me draw it for you. You got a little minus 12 here, and you got a plus 60 here. And you know what that makes? That makes 72, doesn't it? From here to here is 72.
Yes, Professor, I get that.
And see, halfway between there,
Oh, that's the 36?
yeah, that's the 36. Thank you so much for asking. See, that's 36 and 36.
So that's the radius of the X direction?
Yeah. Yeah, it's really not a radius, so the
Or
radius,
the middle of the...
yeah, you got it. The radius turns out to be 60. Okay, now I can tell you this, it's a little bit like an Easter egg. It should be more perfectly round, but I tried. I think it's a little bit more like, maybe like that. That's not too bad. Now this right here is important, guys. That's your maximum normal stress. Actually, we're going over time here. I'm keeping you guys over time here, but you'll give me another 3 or 4 minutes, won't you? Maybe?
Why not?
Yeah, sure. Okay. I can tell you what the maximum normal stress is. I think. I need to find out where this is, though. It's I need to know where that point is. This was minus 12 here, and that's a plus 60 here, and there's 72. No, the 60 is here.
Shouldn't it just be 36 minus the 60? So it's
Yeah.
24.
Yes. Good thinking, Batman. This point right here is 24. And if you subtract 36 from 24, do you get minus 12? And you know, you do. Good going. Okay, so I can tell you what this is. It's 24 plus, should be 60. Because didn't we say the radius is 60? Yeah, I think that's right. It should be 84 KSI should be your maximum. We ought to check it though. And that's the maximum normal stress. Now but now wait a minute, that's the maximum tensile normal stress. there's also a maximum compressive normal stress right here. See this place right here? We got to find what that is. Well, wouldn't it be minus 12? Isn't that what we said?
Negative 36.
No. No, it's 24. It's 24 minus 60. What's 24 minus 60?
Negative 36.
That's what you're trying to tell me. It's negative 36. We think the maximum compressive stress is a negative 36 KSI. Now, if you want the maximum tensile stress, that's right here. That's 60 KSI. So we got all of our maximum stresses. Now, you can take those stress transformation equations and you can plug in. But now here's the catch. You got to figure out what this double angle is. You guys have already figured it out. I think it's 5313, the double angle. The 2 theta. Isn't it 5313? See here's your anchor point. We should do that. We should plug that in and see. Let me find that equation. I've lost it temporarily. And we're going to plug it in. We got room down here. Here we go. We're going to find our normal stress. And it goes like this. Need a little room here. Now what we're going to use here for our angle is 2 theta. That's going to be the 5313. All angles are measured from this anchor point. Okay, let's plug in our numbers. This is 60 plus, oh, wait a minute. That's a negative 12. What's 60 minus 12? 48, isn't it?
Yes, Professor.
Yeah, 48. 48 divided by 2 is 24. 24 plus. Now this is 60 minus a minus 12. Well, that's 72. So that divided by 2, that's 36. Cosine of 2 theta. And we think that this 2 theta, if you want to find this maximum stress, that's the most important thing on this diagram right there. It's a maximum normal stress. That's important too. Sometimes compressive stress is important. But this is going to be 5313 plus 48 times the sine of 5313. Now, if we're very, very lucky, we're going to get this answer of 84 that we already figured out. Plug this stuff into your calculator and let's see what we get. Here we go. 24 plus 36, 5313 cosine plus 48, 5313 sine. Boy, Jove, I'm getting 84 KSI. That's what we figured out. That's the maximum normal stress. It's 84 KSI. You could use the stress transformation equations to find this negative 36 KSI and to find this 60 KSI shear stress. But it's sad, but our time together is coming to an end. Are there any last comments or questions?
No, Professor. I like this wheel method a lot more than doing the bad, very long equation.
Yeah, I do too. It's
I
nice.
had a question
Yes.
on the Moore circle, like the PDF file. On
Yeah.
number 3, there's no normal stress in the y direction, so is it 0?
Yes, very good. The sigma little y underneath is 0. Good going. Is that Kristen? Is that Kristen talking?
No, this is Caitlin.
Hi, Caitlin.
Hi.
So it's just 0. That's an excellent question, and I'm still listening. I guess that's okay, guys. I'm gonna click on this. Yeah, go ahead.
I asked you a couple class periods ago if how I submitted it on Blackboard would work for you. You graded it. You didn't say anything. I'm assuming that was a yes.
How
Like how visible it was. This is Ross.
okay, Ross, how
visible my homework was.
I think I was able to see your homework. I remember looking at it, and I think I was able to see it.
Okay.
I think it was okay.
All right. Cool deal.
Cool deal. Anybody else? Okay, well, I'm going to move this cursor over here to where it says end meeting. And I'm counting down 5, 4, 3, 2, 1. It's over. Bye-bye.
Bye, Professor Griffin.
End
See you
meeting.
in a little bit.
See you. Yeah, I'll see you at 1 o'clock, won't I?
Yes, sir.
Yeah, good.